Hi everyone, today we're going to try to finish off 3.3. So if I remember correctly, the last thing we talked about was how do we form a differential equation using linear operator. So I think yesterday video get end at this point right here, where we have this example of a differential equation that formed by using linear operator. Now, as you can see, this equation right here, or this equation at the top, the generic form, have a lot of letters and a lot of things in it. So usually what happens is the following, is that we write it this way instead to kind of make it easiest for us. So I'm going to go and show it to you before we move on. So most likely in this case, like this equation right here, we're probably just going to write it as this. We'll actually drop the u parenthesis x, so that way we don't get too confusing, and it's basically kind of make it look like we have two separate variables. One of the variables is u, the other one variable is x, but the problem here is to understand that u is a dependent variable and x is the independent variable. Now for this equation right here, sometimes we're just going to write it as this. So as you can see, if you write it this way, the equation is a lot cleaner. And you just have to realize that you have P and Q and R. All those of them are just basically functions of X, but they don't change. And then F also, but then you also have U, which is something that you don't know. You don't know what U function U is. Okay, and when we do more of this, you get used to the notation and understand how they work. Most of the time, when we're doing differential equation, we actually don't write the independent variable. Like in this case, or in this case, we don't specifically write out the x unless, like, of course, you have the function involve x in it. All right. So as I say, the more you do it with this, when we get into chapter 10 and we start solving differential equation, you see how all these things get put together. So right now you just look at all these different methods, different concepts, but you don't know how they link together yet. But once we get through 10, 11, 12, and 13, then you will see how all this stuff get together. So to finish up 3.3, the last concept I want to show you is this one. And as you can expect, mathematicians like to have an inverse. So if I have a linear operator, do I have, is there a linear, is there a inverse operator involved? And is the inverse operator also linear, which is probably the biggest question, because we want everything to stay as a linear operator, so that way whenever we do things, we can apply concept of linear functions to help us out. So let's quickly talk about what does inverse stand for first. So suppose we're given f that map from v to w, and let's say if f has an inverse, then we can say that f inverse map from a subset or subspace of w back to v. Okay, the reason why it doesn't have to be the entire w, because we don't know whether function f actually take up every element in w as an output. So therefore, that's why you only form a subspace. Okay, and also this is true, is that if you take the function f and put in the f inverse of, let's say, the output of f, then you just get the output of f. And if you take f inverse of f of vector x, then you just get vector x. So is that any different than what you have learned before? Well, no. I mean, you learned inverse function back in probably algebra 2. The only difference here is that we could have a vector y and a vector x being different. Instead of when you learn it back in algebra 2, the statement is f of f inverse x equal to f inverse of f of x. But here, because the domain and range could be two completely different objects, unlike what you learned back in algebra 2, where you have functions that go from real number to real number, so therefore that's no concern. But here we have functions that could go from one kind of vector space to a different kind of vector space, and therefore the input and output, the x and the y, could be completely different. Therefore you have to have two separate statements for it. So what do we know about this inverse of a function? So obviously, number one, I did say if have an inverse. So how do I know f would have an inverse? Well, that would be explained in theorem 3.3.6, which states the following. If f is linear, then this is how I know f inverse exists. Then f inverse exists if and only if f of vector x equal to 0 vector has only one solution, and that solution must be the 0 vector. So if you recall, that basically means that the function f is 1-to-1 if it satisfies this condition, that f of vector x equal to 0 vector only have one solution, which is 0 vector. Or in other words, f of 0 vector equal to 0 vector is the only way to get the output 0 vector. You cannot have f of any other vector equal to 0 vector. And it could be very confusing because in some cases this 0 is just the number 0, as in real number, but it could also represent a 0 function, which is basically a function z of x equal to 0. In our case, actually, most likely we refer to the 0 vector as z of x, which is z of x equal to 0. Now, then the question then would be the following. So now that I know how to determine if a linear function have an inverse, then what next? Well, we also need to know that this inverse is linear. So this is what 3.3.7 states. So it states the following. If you have a function f that met from v to w, and let's say f is linear, then let's say f, the image, the image of f is a subspace of w. So if you have a linear function, then the image of the linear function must be a subspace of the range, which in this case, you might think, can it be the entire range? Yes, it can. And the word subspace does not exclude that. So that's the reason why we can use that. Because subspace could be a space that equal to the subspace, the original vector space that is formed the subspace. Meaning in this case, f could be exactly the same as w, or could be something smaller than w. Okay, and if you remember learning it back in 3.2, if it is indeed smaller than w, it's called a proper subspace. If it is as big as w, then we just refer to a subspace, but it's not proper. And if it's 0, if f have only one element in it and the 0 vector, then it would be a trivial subspace. Okay, now here comes the important part, which says the following. If f is 1-to-1, that would mean that f of vector x equal to 0 vector has only one solution, which is vector x. Then f inverse is also linear, and f inverse would go from capital F to V, because we take the image of f as its domain and now map back into the domain of the original function. So show you some example to illustrate this concept. Okay, so here's the first example. Let's say we define a function f that map from R2 to R2. So very easy function. It's not in any weird vector space. Be a linear function. So now important to understand. Ready? In this case, I will probably refer to f as a linear function because it actually work on vectors in Rn. So we can treat it as a function because its input would be a list of numbers. So that makes sense. And we'll mostly refer to a linear function as a linear operator when its input is a function itself, so as not to confuse that we have a function on a function. So that's the reason why sometimes you see me using the word operator, but yet we will define it kind of like this. Like in this case, when I say f go from v to w, if v and w both are Rn or Rm, then I would say f is a linear function. But if, let's say, this function f go from v to w is continuous function space to continuous function space, then I will actually refer to f as an operator. So that way it won't think of it as a function, because I probably want to refer to the input also as a function. So I know it gets very confusing, but that's probably what that will be what I'm going to try to do. So that way there will be a distinction. Operator is a linear function that operate on functions. And then when you have a function that operate on just real numbers or like vectors of real numbers, then we usually just refer to as a function. And that's it. All right. So let's say we have a function f that map from R2 to R2. Let's say it is a linear function, and we'll define this linear function using a matrix defined by, let's say, f of xy is equal to 2, 3, 1, 2 xy. I'm going to ask you to apply theorem 3.3.6 to show that f has an inverse. And I'm going to go and ask you to find the inverse of f. All right, so take a minute to try it out, and you can pause the video and then give it a try, and then see if you can figure it out, okay? But I'm going to just continue. So I'm going to go ahead and do the problem. So if you want to do the problem yourself, you should definitely pause the video so that way you can do it first and then see my answer to make sure that you do it right. So let's show that it is one-to-one first. So how do I show that it's one-to-one? Well, that would mean that I have to show this is true. I have to show that if I do f of the 0 vector, I have to show that f of xy equal to 0 vector imply that xy must equal to 0 vector only. Oops. Okay, it cannot have any other solution other than the 0 vector. That's basically what I mean. So nothing to it but to give it a try. So I'm going to go and say, let's say f of xy equal to 2, 3, 1, 2 times xy. I'm going to set that equal to 0 vector, which is 0, 0. So therefore, that implies that if I multiply this out, I have 2x plus 3y equal to 0, and x plus 2y equal to 0. Now, it should be pretty clear as to what happened here. And we'll take the second question and just say, well, x equal to negative 2y. And I'm going to go and plug it into the top equation. That means 2 times negative 2y plus 3y equal to 0. Oops, I don't know where that line come from. Equal to 0. And that would just mean negative y equal to 0. And that implies y equal to 0. And if y equal to 0, that means x equal to 0 also. And voila, the only solution here in this case is that xy must equal to 0, 0. And there is no other solution other than this one. So therefore, it tells me that f of xy is 1-to-1. And it has an inverse. So now how do I form the inverse? Well, so simple. You remember learning in 3.1 that if you do have an inverse of a linear function in matrix form, and then you must, you can just simply form the inverse by using the inverse matrix. So in this case, I can say that we have the matrix 2, 3, 1, 1, 2. Did I write it wrong? Oh no, okay, good. I was worried I wrote it wrong. 2, 3, 1, 2. So what happened to the inverse of it? Well, that would equal to 1 over 2 times 2 minus 1 times 3. So that would be what? AD minus BC. And then I have to flip-flop these two numbers. So these two numbers are actually the same. So when I flip-flop, it's the same. And then negate the other two. So it will be minus 1 minus 3. So just so happen 4 minus 3 is 1. So therefore it doesn't change. And so just 2, negative 3, negative 1, 2. Okay. And it shouldn't be too difficult for you to just simply look at this and just multiply this matrix right here with 2, 3, 1, 2, and then you should be able to see that they can multiply to the identity matrix. So therefore now what is the inverse function F inverse? Well, F inverse of xy would just equal to 2, negative 3, negative 1, 2 multiplied by xy. All right, pretty straightforward. Now let's try a different one. How about we do this one? We're going to go and let f, oops. All right, we're going to go and let f go from R to R2. And let's say the function f is this, f of t equal to tt. I'm going to put down these 3 questions for you to look at, and then we can probably go over in class, or someone feel comfortable posting his or her answer. That would be great. So is the function f of t linear? B. Is f of t 1 to 1? And C, well, actually you can probably guess that f of t is 1 to 1 because of what I'm going to ask you to do in C. I'm going to ask you to find me f inverse and state the domain. And when I say state its domain, I mean state f inverse domain. All right, so I'm going to go and stop the video here. So this video is short. Retrospect, I can probably put like 10 minutes from last video into this one, and that way they kind of balance out. But sometimes I don't know exactly how long the video is going to be, so sometimes hard for me to do that. So this video is going to be like 18 minutes long, which is great. So give you a short video for a change. Try to do those 3 problems. We can talk about during class. All right, I'll talk to you guys soon. Okay, bye bye.